We have seen how to compute the area of a region below a graph of a positive function. And now let us consider a slightly more general case if we have two functions with two graphs. Imagine a situation like that. Two functions, one is denoted f and the other g, and two values a and b, and we want to find the area of this region. One possibility is to consider the area below the graph of f. This is this large region, and we subtract what is below g, minus integral from a to b of g of x dx. But this can be written in a shorter form, namely integral from a to b of the difference f minus g dx. And this is a result good to remember, or good to know. Let me consider an example. So this is the area of this. Let's consider the two functions, f being, say, x squared, and g being, say, x cubed. And what about the endpoints, the limits a and b? The problem may sound like that. Consider the area bounded by these two graphs between the intersections of the two curves. So first we want to find the common points, the intersections. In general, the intersections will be found by solving the equation f is equal to g. Well, for this simple case we can guess the result without any computation, right? Because x squared looks like that and x cubed looks like that. And they do intersect at the origin 0, 0 and at the point 1, 1, no problem. Okay, let's complete this approach if it is not possible to find a solution using the picture just by heart. F is x squared and g is x cubed. Once again, this equation is so simple that we can easily guess the solution without any computation. But let us see how we should proceed if it is not so easy, if it is not obvious. We can consider the difference, and it's usually easier to work with products than difference. So we factor out x squared, and we have x minus 1. And now, product is equal to 0 if at least one of them is equal to 0. So first, if x squared is 0, then x is 0, or if the bracket x minus 1 is 0, that means x is 1. And this is the complete set of solutions of this equation, and this is the complete set of intersections of these two curves. Perhaps someone might suggest that they intersect also on the left in some negative x. Do they? No, they don't, because x squared goes up and x cubed goes down. No more intersections. So we have only these two, exactly these two intersections. And then this area, A, will be integral from 0 to 1. These are the points where the curves intersect. Oh, and now we should take the greater function minus the lower function. Otherwise we would get a negative result. And greater function between 0 and 1 is x squared. Now the antiderivative of x squared is x cubed third. The antiderivative of x cubed is x to 4 divided by 4 from 0 to 1. At 1 we have 1/3 minus 1/4 minus 0, which is 0. And this can be written as, if we bring the two fractions to common denominator, we have 12, and 4 minus 3 is 1. Once again, it's a good idea to check this result roughly. This area is definitely bounded by this square, which has area 1. Half of the square has area 1/2, but some points are missing here, so this moon-like region has a small positive area. If we make a mistake and if we write the two functions in an opposite order, which is the wrong way, but let me illustrate where it goes. If we write integral of 0 from 0 to 1, and if we write the bad order x cubed minus x squared, then we have x to 4 divided by 4, x cubed third from 0 to 1, and then we have 1/4 minus 1/3, which is now minus 1/12. If we started the line by A is, meaning the area, then this is a bad result. Area shouldn't be negative, and we have A is negative. So we have two ways how to correct this small mistake. Either we write minus in front of each expression, If it is a sum or difference, we must close the expression in brackets. Or possibly, we don't write A, we just compute this integral as some useful result, and after that we write A is minus the integral which is the positive value. Or a third way, if you like, don't use the red version, don't use the green version. If you don't want to write minus here and here and here and here and here in many places, it's perfect enough to write the minus just here. And then minus A is minus 1/12, and then A is 1/12, right? Or still another solution would be to close all the integrands in absolute values. But definitely the best way is to consider carefully which function gives greater results in the interval of interest and write the greater function minus the lower one.